right, everybody. Might have to pause here to let some more people in, but I'll start getting started. Welcome everybody to the Robert Ferguson Observatory Speaker Series. My name is Stephanie Dromelar. I'm the Executive Director of the Observatory, and we're so thrilled and honored to have Dr. Raffaella Margutti with us today, and I'll introduce her in a moment. But before we start, just want to remind everyone to keep yourselves muted to minimize background noise, and Dr. Margutti is willing to entertain questions throughout her talk. So she asked, feel free to either put questions in the chat, or she's also okay with you muting yourself if you have a question while she, before she kind of moves on. So you're welcome to do that. And if you put them in the chat, then I will go ahead and facilitate asking her those questions. And then we'll probably have some time at the end, I imagine, too, for some questions at the end. So just real quick about the Robert Ferguson Observatory. I see a lot of familiar faces and names, but for those who are not familiar with us, the observatory is run by the Valley of the Moon Observatory Association, which is a 501(c) nonprofit comprised of volunteer, amateur, and professional astronomers. And we fulfilled our mission of offering educational programs about science and astronomy for students, the public, and in support of educators for about a little over 25 years now. The observatory is almost all volunteer run and typically serves about 9,000 visitors annually. We're located in the beautiful Sugarloaf Ridge State Park up here in Kenwood and Sonoma County. And the observatory houses a 40-inch reflector telescope, the largest telescope in Northern California that's accessible to the public, a robotic 20-inch research grade or CCD telescope, and an 8-inch 2-meter-long refractor telescope. Sorry, letting a couple more people in. We have a great, we truly are a public observatory. So we have a wonderful volunteer program if people want to become docents and learn how to use our telescopes and work with the public and offering educational programs. You can fill out a volunteer application at rfo.org if you're interested in that. Membership is another great way to support the observatory, and there's all kinds of fun membership benefits that our members get. Also wanted to add, we've kept the presentations in our speaker series free to the public to align with our mission of offering educational-based astronomy programs to our community. That being said, if anyone is so inspired to donate to the Robert Ferguson Observatory to ensure that we can continue fulfilling that mission, you can do so through our website, rfo.org. And I'm sorry, I'm just going to mute a couple people here. Okay. So to introduce Dr. Raffaella Margutti, she received her undergraduate degree in astrophysics in 2006, magna cum laude, and her PhD in physics and astronomy from the University of Milano Bicocca in 2010. Margutti is a Sloan Fellow in Physics, a CIFAR Global Scholar in Gravity and Extreme Universe, and received the 2022 New Horizons in Physics Prize for leadership in laying foundations for electromagnetic observations of sources of gravitational waves and leadership in extracting rich information from the first observed collision of two neutron stars. She's currently an associate professor of astronomy and physics at UC Berkeley, which I think is where she's calling in from now. And her research is positioned in the new field of multi-messenger astrophysics with gravitational waves. Margutti and her research team utilize observations of the most violent transient astrophysical phenomena in the universe, including stellar eruptions, stellar explosions, mergers of neutron stars and black holes, as well as stellar tidal disruptions by supermassive black holes. So without further ado, I'm going to pass it on to you, Dr. Margutti.
Thank you so much for having me. And I'm really impressed by all of your efforts to support education in STEM and astronomy. So, I mean, really, thank you so much for doing that. Okay, let me see if everything is in good order. So right now you should be seeing my screen. Is that right?
Yes, it looks perfect.
Perfect. Yes. So as Stephanie was saying, please feel free to interrupt me. I know that sometimes, especially with things remote, it might look like I'm talking to myself. So please, let's try to have a conversation. Any curiosity that you might have, please don't feel nothing should stop you from just asking me. So I gave this title of the Renaissance of Astrophysics, and I know that for some people, the reaction that I get is, well, we're not dead. Why you're talking about the Renaissance? And here's what I mean. So I believe we are living in a very, very special time in astrophysics. And the reason is that there are boundaries among different disciplines. And specifically what I mean is like the hardcore particle physics with gravitational waves, and those that do studies with photons. Those boundaries are being torn down, and this is an amazing time to live through. And these walls that are falling are basically allowing cross-pollination among different disciplines, which was one of the engines behind Renaissance in my beloved country, Italy, where I grew up. Okay, so let's start chatting about this world of what I will call multi-messenger astrophysics, which is the world where we can use gravitational waves, and I'm going to talk about what these are in a second, and light to understand our universe. And what I want to emphasize since the beginning is what we do not know. So where is the boundary of our knowledge, which is effectively the good ignorance, which is the fuel behind any research. And in the world of stellar explosions, we do have some pretty big question mark that you can see right there on this slide. So we do know that massive stars that are, let's say 10 times the sun or more, we do know that they explode, and we do know that they produce sometimes a neutron star, so a very, very compact body, or a black hole, even more compact in that case. But we don't know right now, I can't tell you which star is going to produce what. So we do not know what produces what. We do not know how these black holes and these neutron stars behave right after they're born. So this is one of the big question marks that we are working on right now. What we do know for a fact, though, is that massive stars like to hang out in binaries. So the most likely situation for a star that is 10 times the size of the sun is not to be alone, but to have a companion. So the most likely scenario, like 70% of the stars in the galaxy are together in binary systems. So what happens is that the most massive of these two stars will be the first one to explode as a supernova. And let's assume that this will produce a neutron star. After a while, the second star, less massive than the primary, explodes and produces also, let's assume, a neutron star. And what we do know for a fact is that these systems, these binary systems of neutron stars, they can't stay there rotating one around each other. We will understand why. But what has to be happening at some point is a collision of these neutron stars. And what we can do right now is to study this type of collisions, which are among the most violent events you can think of in our universe, not only using light, but using also gravitational waves. And the big question mark that we are trying to address here is what happens during this merger and what type of light this event might produce or might not produce. So the message here is that we do have quite a large knowledge gap, but we also have a unique opportunity to fill that gap with observations. Those are the common observations that we're used to. So we use photons, we use electromagnetic radiation, just another way of saying photons, across the spectrum. So we use radio, we use UV, optical, X-ray, gamma rays. But now we live in this special moment in time where as humans, we can use neutrinos, so particles, including neutrinos, and gravitational waves. So the main message here is that we have a unique opportunity to try and answer some of these questions. So here is the story that I want to talk to you about tonight. So we will talk about the story of two neutron stars, and we will learn how to produce one neutron star, two neutron stars, and these two neutron stars merged and produced and were detected on 17th of August 2017 as the first and only, I want to remark, also the only celestial object for which we have gravitational waves and light. But here is the story, and this is an artistic impression, it's not a reality. And I believe there is also some sound that is kind of funny. That's what NASA thought it was cool to have. So let's see what we will be talking about tonight. Apart from the sound that was very dramatic, I wanted you to have an idea of what I will basically explain to you, which is what happens when two neutron stars merge. And the way I wanted you to have a little big picture so that you'll likely be able to follow me better. But also, I want to tell you this story not from just from a purely scientific perspective, but I also want you to appreciate how we did that discovery. So what happened during that day, how we organized our facilities, so that you can appreciate also the life of a scientist on a day-to-day life, which I personally believe is also very interesting. So let's start to give you some context so that we all understand what type of context, what did we know all the way to that morning of August 17th, 2017. What did we know, what we were expecting, so that you will be able to understand better how the decisions that we took that day. So first of all, we need to form one neutron star. And this is easy. And again, you're looking at an artistic impression that will look likely very familiar at the end. So it's easy to form one neutron star, and that is the result of one stellar explosion. So the animation of the previous slide would have ended on an image of this supernova remnant that I'm sure a lot of you are already recognizing as one is the explosion that happened in 1054 after Christ. So we do know very well how to form one neutron star. Why? Because we can point our telescopes and look there. So here is what is left behind after 1,000 of years after the stellar explosion. We're looking at the Crab Nebula, and you can see how that looks at different wavelengths, from radio on your bottom left all the way to the gamma rays on the bottom right. And that source, that point source in the gamma rays, that's a neutron star. So we did know very well how to produce one neutron star by exploding one massive star. That was known. So the thread number one is how do we produce one neutron star? Yes, we knew it. Explode one big star, and you have it. But as you know, we are talking about the merger of two neutron stars, so we need two of them. Well, in that case, we need to start, one of the ways is to start with a binary system. And as I said at the beginning, the most massive star will use its fuel, has more fuel to start with, but it will use it much faster than the less massive star. So as a result, it will explode earlier. So the lifetime of a big star is shorter, significantly shorter than the lifetime of a star like the sun. To give you an idea, a very big star would live like a few million years compared to the billions of years of the sun. So we have the first explosion from that is produced by the most massive of the two stars. We wait a little bit, and we form the first neutron star, which is that gray dot right there. We wait a little bit, and the second star also explodes. And here we are with a system of 2 neutron stars. However, it's not that simple. As you might have guessed, it's not so simple to stay with your companion when your companion is exploding, right? So there is a large chance for that system to be entirely disrupted by the explosion. And so here we have a system that first of all, has to survive not 1 explosion, but 2 explosions. So doing numbers, it turns out that only 1 system out of 100,000 of these systems that were born with some good chances to produce 2 neutron stars, only 1 out of 100,000 will make it to the end as a bound system of 2 neutron stars. So the message that I'm trying to send to you is these mergers of neutron stars are rare. They are extremely, extremely rare occurrences in our universe. And we knew that going in. But let's assume that we got lucky and our system was able to survive until the end. And so we are now at the position of having 2 neutron stars. Now, why those 2 neutron stars could just stay there forever rotating around each other? Why that is not possible? And the answer to this question is in that plot, in that graph that you see on this slide. So on the y-axis, you have a quantity that is quantifying how close the 2 neutron stars are getting to one another. Forget about what that quantity really is, it doesn't matter, but it's telling you how close the 2 things are getting. And on the x-axis, you have the year. It's literally the calendar year. And you have some data points. Those are the dots are real data points. They're measurements with radio frequencies. And then you can see the prediction of general relativity with the thick line. And I want to emphasize, this is not, I'm not trying to reproduce the data. This is literally the prediction from theory. And as you can see, general relativity, the theory of Einstein, is telling us that what we are seeing with data has to be expected. It has to be expected that this system of 2 neutron stars is rotating around each other, yes, but the distance between the 2 neutron stars is decreasing with time. Why? Because this system is losing energy through gravitational waves. So we can see gravitational waves, but now we can detect them with the gravitational wave interferometers. So back in 1993, this discovery was worth the Nobel Prize. So in 2017, we did know very well that a system of 2 neutron stars could not survive forever. But why? Because they were losing energy, and they were doing so in excellent agreement with the general relativity theory of Einstein, which meant that we did have very good reasons to believe that gravitational waves were produced by these systems. So threat number 2, for binary neutron stars, the orbit shrinks. Why? Because the energy is lost in what? Gravitational waves. All right. Threat number 3. So since the 70s, it was known that in the universe can produce some flashes of gamma rays that are known as gamma ray bursts. And these sources have a very interesting historical, they have a very interesting story. And so first of all, they were discovered by accident, entirely by accident, in the sense that in the 60s, it was a very delicate time, it was decided that some satellites, and the Vela satellites, were put on orbit to detect gamma rays, yes, gamma rays, but not from the universe, gamma rays coming from nuclear explosions, nuclear weapons on Earth. So gamma rays are one of the byproducts. If you explode some nuclear bomb on Earth, you would detect gamma rays, and that's what these Vela satellites were aimed at. And they wanted to know if somebody on Earth was experimenting with nuclear weapons. So they started detecting gamma ray bursts, and for a few years, these detections remained military secret. And it was only in 73 that the discovery was published in a paper by Kleeb-Seidel, where they realized that these gamma ray bursts were coming from all over the place, from the entire sky in a homogeneous, high isotropic way. And that was a very good observation that was telling very clearly that these gamma rays were not of human origin, but it was the universe producing them from very far away. So these gamma ray bursts remained a mystery of what could produce these very short but very intense pulses of gamma rays for many years. And to give you an idea, the amount of energy that is released in a gamma ray burst over a few seconds is the equivalent of what the sun will release over its entire lifetime. So over a few seconds, take the sun, let it go for its entire life, and put all of that energy into 3 seconds. That's what a gamma ray burst does. So after decades of studies, we knew. So we knew in 2017 that one possibility, or at least we speculated that one possibility to produce these gamma rays was indeed the collision of two neutron stars. That was speculation, was one of the theories, and we had very good reasons to believe that that was correct, but we didn't have any smoking gun that was the only explanation and the explanation. But for sure, that was a theory right there. All right, so far, what did I tell you? So far I told you how to form one neutron star, how to form two neutron stars. I told you that these two neutron stars can't stay there forever, but they have to collide. And that when they collide, we had very good reasons to believe that something very violent would happen, and maybe producing gamma rays. Let's now, and this is a summary so far, right? We have couples of neutron stars in the universe. They are very rare because we can disrupt the system quite easily. But when they survive and they have to merge, and something violent is expected in that case. Let's now add the last thread, the last thing that we knew back in 2017. So when I was a graduate student, it's been a while, but when I was a graduate student, the theory was that we could form the heavy elements in our periodic table. And when I say heavy elements, just focus on the elements after iron. So iron is number 26 right there. So we thought that we could produce all the heavy elements of the periodic table just using stellar explosions, and that was more than enough to do everything. However, if you look at this slide here, you can see that we have a lot of places where the orange is now appearing, which is the merger of two neutron stars. So before 2017, there were a number of seminal papers that started thinking about the possibility that some of these heavy elements, and when I say heavy elements, let's translate that into something concrete. Let's talk about gold or platinum, anything that maybe you're wearing something, some jewels that are jewelry that is made of that. So those heavy elements, we thought they were only produced in stars, but before 2017, a new theory started to come out, and which was that maybe some of these heavy elements are not coming from stellar explosions, but they are indeed coming from mergers of neutron stars. And again, this was a very good, there were very good theoretical reason to think that that could be the case, but we did not have any observation to prove that, right? Okay, so these four threads which come from very different worlds of astrophysics, they were united entirely in one single event, which is what happened on August 17th, 2017. So, as I said, I want to tell you the story of this day, and here is how it all started. So, right now we have a new type of telescopes on the interferometers, gravitational wave interferometers, that can actually detect these gravitational waves as a result of basically space getting deformed by basically the gravitational wave that is coming from this neutron star merger. And what you have on this slide is how this gravitational wave look like, depending on what system you're looking at. And so far, we do have the capability to detect gravitational waves, but only from the most violent of the things you can think of. So we can detect black hole mergers, and we can detect neutron star mergers, basically. And before the first detection of gravitational waves is from 2015. And is 150914. And then the naming is, as you have guessed it already, the year 15, September, and then the day. And GW stands for gravitational wave. Forget about LVT for a second here. So all until before 2017 and before August 17, 2017, all we had seen were these black hole mergers. And now let's play the movie of the gravitational wave signal associated to this event, GW17817. And here is how it looks. And there are the line is going up and down very, very, very fast. And it takes no astrophysicist to say that whatever 17817 is, it's strikingly different from all we had seen before, right? Look how short the signal from black hole mergers was, and the neutron star merger after 30 seconds is still there, is still going. So again, it doesn't take actually nothing to say, well, whatever is 17817 is something we have never seen before. And this is how the day started for us. We received an alert. That's how it goes. We receive an alert on our cell phones from, and you heard the chip, and that is whoop, is when the two neutron stars merge. So we received an alert on our phone saying that the LIGO and Virgo gravitational wave interferometers had detected something with properties that look like nothing they had been observing until then. And it was soon realized, because we knew what to expect in case of neutron star mergers, that one possibility was that maybe we are observing with gravitational waves for the first time a neutron star merger. So if we were to place the masses of the things that are colliding on a plot, here is how it would look. You have on the y-axis, you have the mass of these two objects that are colliding in units of solar masses. So the two neutron stars that were colliding in 17817 had roughly the mass of 1.5 times the mass of the sun. And those are the two big stars. I emphasize them with the yellow stars right there. And they merged to produce something that we think is a new black hole, but we do not have a direct proof that what was formed was a new black hole, to be fair. But as you can see, there seems to be like two different worlds, the worlds of neutron stars with masses of between 1 and 2 solar masses. And then there is the world of black holes with masses above 5 solar masses and all the way up to 100 and more solar masses. So let me now tell you the story of how things happen on that day. So it's 6 a.m. I'll tell you the story from using as time in Pacific. So it's 6 a.m. and we received the LIGO alert, LIGO Virgo alert. It really comes in on your phone. And if you have any interest of getting paged about new discoveries, you can download the LIGO app, and LIGO is gonna restart in March 2023. So you can actually stay updated and see what this LIGO Virgo interferometers are detecting in real time. It's kind of fun. All right, so at 6 a.m. We get the alert on the phone, and we understand very quickly that this is a very unique, extremely unique event, never seen before in the world of gravitational waves. But 2 seconds afterwards, something very special happens. And here you have a graph, and let's focus on the bottom panel. So before I showed you the little wiggles of gravitational waves, which is a sort of an artistic rendering of how a gravitational wave looks like. What you have, that plot on the bottom, is how one way we can actually scientifically accurately visualize the gravitational wave signal. And you can see the signal starts from negative time, because time 0 is when the 2 neutron stars have collided. And as you can see, the frequency of the signal goes up, and you can map that in your brains as a y, because the 2 neutron stars are rotating faster and faster around each other. And then at T0, the two neutron stars have merged. And that's the end of the gravitational waves that we can detect. But 2 seconds afterwards, the gamma ray spacecraft tell us, hey, there is a burst of gamma rays. And 2 independent spacecraft tell us that the integral and Fermi. So 2 seconds after the gravitational wave event, there was a gamma ray burst. Great, but having things that are happening at the same time doesn't mean that they are actually physically related, right? So let's place the gamma ray burst signal and the gravitational wave signal on a map of the sky. And what you have there is with the in green, you have the map of where the localization, we say, of the gravitational wave signal. And as you can see, if you use the LIGO only interferometers, which are the US-based one only, you would end up with 2 banana-shaped regions, one in the north and one in the south. And combining that signal with another gravitational wave interferometer, Virgo, which is in Italy instead, you can reduce the uncertainty to a much smaller one with the darker green. Now, this is where most likely the gravitational wave was coming from. And if you then overlay where the gamma rays were coming from, you would end up concluding that according to the Fermi spacecraft, they would come from that dark blue area of the sky. According to the integral, IPN Fermi integral localization, they would come from that stripe. So the bottom, the important message here is that all of these regions of localization agree that from that part of the sky where they all intersect, something is happening, both on the gravitational wave part of the world and in the gamma rays. And I think that some of you have a lot of experience with observing, and I want to give you an idea of how big that localization region is. So gravitational waves are not easy to localize. So in this case, we got lucky, and they were able to tell us to look for something within 28 square degrees of the sky. And to give you an idea, is picture in your mind a full moon, multiply that times 100, and that put all of these 100 moons next to each other. That's the region in the sky that we were asked to search for any counterpart at the time of the merger. And let me tell you, this is extremely challenging because in 28 square degrees in the sky, there are a ton of galaxies. A lot of things can fall there. So it's almost like telling you, go and search for something like a needle in a haystack. So here's what we did. So it was early morning when we understood that we had to do that search. This is the event we have been preparing for many, many years. We understood that is the time and we need to get into action. But none of us, of our team, not other teams on this planet, had access to any telescope where there was night. So we had to wait 11 hours before having the night on any of our locations. And specifically for the team, for my team, we had access to a telescope in the south in Chile, which was great because this event was is in the southern skies. So we had 11 hours to wait. And here I'm just saying waiting. In reality, those were the most hectic 11 hours probably of my life. What was happening was that we kept asking the gravitational wave community to tell us a refinement of their coordinates. Tell us your best localization. And the localization was shifting in the sky as the time was approaching the time of when the sun would set. And every time the localization of the gravitational wave people was changing, we had to replan. So that's a telescope that actually we used as DECAM in the southern skies in Chile. So here is our team was organized. And again, it's something that we have been planning for quite a long time. So we had a good team set up. So the idea was that at some point, the LIGO Virgo interferometers, which look like those two big arms that you see in that picture, would find something. And then we would trigger our DECAM as a telescope that has a very large field of view. So it can image big chunks of the sky at the same time. So it can be fast tiling, basically. And DECAM at some point would find something, and DECAM would be able to localize the source. So going from 28 degrees to like sub-arc second localization, so very, very precise location in the sky, that would have allowed us to then trigger a whole range of other facilities that don't have big eyes. They can only point in a very narrow part of the sky. So looking at this setup, what can go wrong, right? There is a LIGO alert that can find a counterpart, and then we trigger spectroscopy, we trigger our X-rays, we trigger our radio. Clean and easy. Well, reality was a little bit more interesting, if you want. So we're here waiting for the sun to set. And as I said, there was this continuous refinement of the coordinates. So it was extremely hectic. We're using this telescope. And after half an hour after sunset, our collaborator, Ryan Chornock, that back then was at Ohio, is actually now faculty here at Berkeley. So Ryan sent this email where we're gonna say, holy cow. So he said, check out this galaxy, NGC, blah, 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 is the name of a galaxy. And I want to emphasize that this very, very short email was sent to more than 100 people. So Ryan is a man of few words. He chose them very carefully. So Ryan basically did not trust that all the software that was put in place to find new sources as DECAM images were coming through, he did not trust that that software could do it and could do it in a reliable way. So what he did, being an extremely experienced optical observer, is, well, he started matching the images and trying to play the game of, let me see if I find a new source that wasn't there from the day before, using other images that we had acquired earlier. So what did make Ryan swear? So here is, I'm gonna zoom in a lot in the image, and it's gonna look like the simplest possible thing on Earth. So what you're looking at is an image of the host galaxy, of a galaxy, that NGC blah, 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 that I told you before. And this is before the neutron star merger, and this is the after. Easy, right? If I play it like this, I mean, whoop, there is a new source. Very easy, very, very, very easy. And that is how the discovery of the counterpart and the localization of this counterpart of a neutron star merger happened in the team that had access to DECAM observations. Okay, so that little dot is the first localized light coming from a neutron star merger that was detected together with gravitational waves, the first and the only right now. Great. So what this thing was doing, what this discovery was buying to us, is not only scientifically speaking, it was immense at the importance, but it was allowing us to know precisely where to repoint our telescopes, the ones with that could not have wide field of view. And that's what we did. And when I say we did, this is we, our team, together with hundreds and thousands of other astronomers on the planet. Basically, every single telescope that could point to this source, it did it. So, and as part of our team, what we do to try to differentiate our effort from other teams is that whenever we find something of extreme interest in the sky, we trigger all the facilities, all the observational facility we can put our fingers on. And that includes a whole fleet of spacecraft from both from US side, from ESA side, a whole range of telescopes, and also all our radio antennas. So everything we can put our fingers on. Why? Because each piece of the spectrum, of the electromagnetic spectrum, is actually giving us a different part of a story.
Raffaella, to interrupt. Somebody just asked, can you give us a sense of scale in this image? How far apart are the objects visible here?
There's like, yeah, so the object is a 40 megaparsecs from us, and I think that is 130 mega light years. So it's 130 million years in light years away. So basically, when this merger happened, there were still dinosaurs on Earth.
Wow.
To give you an idea. Yeah, so we triggered everything, and we started collecting information. That's what we did. And here is I want to replay the movie to remind ourselves what we're looking at. And that's the event. We were watching a merger of these two neutron stars. And the light that we were detecting was coming after the merger happens. The beauty of this combination of gravitational waves and light is that gravitational waves tell you everything about the before the merger, and then they stop. Light comes out after the merger. So light tells you what you form afterwards. Gravitational waves tell you where your starting conditions. And that's why it's so amazing that we have both messengers. So basically, the picture that we have to keep in mind is that the light that we were expecting, and I'm gonna go a little bit faster here and get into a little bit too late. So the picture that I want you to have in mind is that we were expecting to find some sort of a spherical light bulb that is actually the place where the heavy elements are formed. And we were also expecting to have some very highly collimated jets of matter. And to give you an idea how fast these jets are traveling is effectively the speed of light. It's just a tiny correction less than the speed of light. So this is what we were expecting theoretically. And so we started getting observations, and I told you we had to wait 12 hours because there was no telescope that could repoint it. But after 1 hour and a half, after we knew where to look in the sky, we could get the first radio information coming in, and we got very excited. At least I got very excited. And when I saw this image, and I got very excited because of that little elongated dot, white dot that is in that picture. That's how a radio source would look like. It's just elongated, it's just because of where it is in the sky, so it's not intrinsically elongated. But then I got less excited when I put down the location of the source that Ryan told me to look at, and it was not on top of the white part. So basically, I didn't have any radio whatsoever at 13 hours. And we kept collecting data. So the optical astronomers were having a lot of fun. They were getting a lot of photons, a lot of information. And finally, after 2.4 days, I managed to repoint Chandra. Chandra is a X-ray spacecraft, the X-ray spacecraft right now that has the best vision, so sharp. It took 2.4 days to get there. And what you're looking at is how the sky looks in the X-ray, and every little square here is a photon, and here is where Orion's source would be, and there is nothing, absolutely nothing. Those two photons that fall inside that region are from the background. They're not even astrophysical, maybe. So nothing. So optical astronomers getting a lot of fun. Radio and X-rays, nothing of nothing. But in the optical, things were extremely interesting, and things were developing in a way that the theorists could predict. So here is a prediction, an astonishingly good prediction by Dan Kazin. Dan Kazin is also a professor here at UC Berkeley, and is a pioneer in predicting what the light, the optical light, should be coming from these neutron star mergers. And what you have in blue and red, the thick lines are his models, Dan's models, and the data points are our observations. And you can see clearly how his models were so good in explaining the data points. So this is the light that is coming from where these heavy elements are formed. And here I can't go into the details, but what I want you to just to know is that those wiggles that you see of how light is distributed in this case in the near infrared spectrum, that precise wiggle is the evidence that this neutron star merger has produced heavy elements. And for me, it's always remarkable to think that, I don't know, if I'm wearing something that is made of gold, that is made of whatever heavy elements is your favorite, well, that thing might have been forged by a neutron star merger somewhere in the galaxy or maybe outside the galaxy. I always find it just mind-blowing to think about that. All right, so again, the optical people were getting a lot of fun for 2 weeks. The X-rays and X-ray and radio were empty-handed. But after 2 weeks, we started getting something. We started detecting something, and da-da-da, those are 10 photons. I can name them, but those are, in my opinion, the most beautiful X-ray photons that we have ever detected. Those are the first X-ray photons that I can say with high confidence were associated with a gravitational wave source. And then things got brighter and brighter, and but after we started getting some fun, of course, the practical life is more complicated, and we have a star that is very close to us. And we're very grateful for that star to be here and providing all the energy that we need. But the sun got into the way, and it just got too close to our source. So for 100 days, we lost information in the optical and in the X-rays. Not in the radio, though. So radio wavelength, unless the source is really behind the sun, they don't really care. So we kept actually monitoring the source in the radio, while every other wavelength was basically just too close to the sun, and we could not refine it without damaging the instrumentation. All right, so long story short, what did we see? Well, what we saw was a large brightening of the source over a time scale of 100 days. All I want you to take home from this plot is that it took 100 days for the X-rays and radio to peak, and then it started fading away. That's all I want you to take home from here. And the reason why it took time to brighten and then decay is very much related to the fact that the X-rays and radio are coming from these extremely powerful jets. But these jets, this jet is very collimated, and when I say so, I mean these jets are collimated to a few degrees, so it's extremely collimated. It's extremely narrow, this cone. So what happened was that we were not so lucky to be inside that cone of radiation, but instead, the most likely situation is that we started observing that source from outside the cone. So what we had to do, so we would say we were not on axis, but our observer was off axis. And so what we had to do was to wait for the jet to basically open up and intersect our line of sight. So at the beginning, I don't see a thing because the jet is not looking at me. But then I wait a little bit and the cone of radiation is going to open up and is going to intersect our observer. So I see the light, and that's when I see the peak of light. So this is the reason why it goes up and down, but it takes 100 days. We need to wait for that jet to decelerate, for that cone of radiation to intersect our line of sight. So just to summarize then, what happened in August 2017, we know it's a merger of two neutron stars. How we do know that? Because the gravitational waves are telling us the story. And we do know that this merger produced heavy elements, and we call the place where they are produced the kilonova. And we also knew, because of the X-rays and the radio, that this system did produce some extremely collimated jets. And also, we do know that this system also produced the gamma rays that we know are typical of a gamma ray burst. So let's do fast forward to now. We had some block for a while, but after a while, the source came back and we could see, we could reobserve this source. We used HST, we used Chandra, we used everything we could put our fingers on. And then many years after the merger, 3.5 years after the merger, we decided to go back and have a look at another pic of the source. And to our big surprise, if you look at the X-ray panel, which is on the left, we have some photons there. There is nothing in the radio. You can see that on the right panel, the orange circle is empty. But in the X-rays, there are photons, and we were not expecting that. So this was a nice surprise that even years after the merger, we were still there and able to detect light from this merger. So the reason why this is exciting is because the presence, the unexpected presence of these X-rays might be related to what we formed. So I told you at the beginning, I can't really tell you what these two neutron stars formed. We think is a black hole, but I'm not sure. And one of the possibilities is that these persistent X-rays years after the merger are a signature of this newly formed black hole. And of course, how we're gonna find out the final answer, we need to keep staring at this location in the sky, and we need to find more of these mergers. So this is why, after 2017, we failed to find any other sign of light from any other gravitational wave source. And the LIGO interferometers will come back online, they say, in March 2023, pending some further delays. So at Berkeley, we are getting really ready to jump in this new era of multi-messenger astrophysics, and to do so, we put together a new time domain survey. It's another of those telescopes that have big field of view that can do that tiling job at the beginning that enables effectively the discovery. And that is LS4 is the La Silla Mid-Southern Survey. That is a telescope that is again in Chile, and that will allow us basically to play that game of tiling the localization region of gravitational waves and finding the counterpart, and then repoint everything we have. So I tried to give you an idea of how that discovery of light and gravitational waves happened during that day, and I tried to give an idea of what happened during that day and how scientists go about trying to play this game of multi-messenger astrophysics. And yeah, I thank you for your attention, and if you have any question, any curiosity, I'm here and very happy to chat with you.
Wow, thank you so much. That's that must have been one hell of a day on August 17th. Oh my goodness. Yeah, that's great. So you weren't at Berkeley yet at that time, right? Was this when you were still on the East Coast, or?
Yeah, so that is funny. So I actually took a red-eye flight from California to Chicago, which is where I was a professor before, and I just landed 1 hour before getting the alert. and I was not looking forward to wake up 1 hour afterwards. But you know, the universe calls you, and my schedule is set by the universe. That's how I like to put it. And yeah, it was the most exciting day of my life.
Oh my gosh, and why is you were saying that the gravitational lab is offline until March? Why is that?
Yeah, so every now and then they plan for upgrades of their facilities. So they do observing runs of on average of a length of 1 year, and then they take some time off to implement some upgrades, and because they want to go deeper, basically, they want to improve on their sensitivity.
Okay. Well, I'm sorry, feel free to unmute yourself, or like I said, you can put a question in the chat. Oh, I think there are some questions.
Yeah, there is a question. Did scientists expect LIGO to detect these events before LIGO came online? Yes, they did. The world of the effort to detect gravitational waves is like a 30 years long effort. And the reason why people were so persistent is because of that finding of the fact that the neutron stars they were rotating around each other, the orbit was shrinking, and was shrinking not in a random way, but just like the general relativity theory of Einstein predicts. And if that was right, gravitational waves had to be the source. So they knew that gravitational waves most likely did exist. But it's a fantastic story of persistence. When you have a vision that is guided by deep understanding of physics, persistence pays back. Yeah.
Wow. There were also a few thank yous. Can you talk about how the new James Webb Telescope will affect your work?
Oh yes. So these neutron star mergers, they actually produce most of their light in the near infrared and infrared. And guess what? That is where JWST is going to blow out of the waters everybody else. So our goal and dream would be to take a spectrum of basically understanding how light is distributed in the near infrared and infrared. Why? Because that is where we will find clear signatures of how much of those heavy elements were forming. So yes, JWST is expected to revolutionize this field. However, for JWST to do so, we need to find where they are. So the gravitational wave localization is not enough for JWST to repoint, because JWST has a very, very narrow field of view. So you need to have an intermediate step where basically gravitational waves tell you, look around here, and then you repoint your wide field of view instrument, and then you refine your localization, and then you send it to James Webb. Yeah, what color would the neutron stars be? So the light coming from the merger is actually the guaranteed light coming from the merger is very red, so infrared. However, and there is also a more like a hotter component that comes all the way to the UV. So there is a little bit of everything for everybody. No matter what is your favorite color of light, your neutron star merger is gonna produce it.
There was one towards the beginning, you had talked about a star exploding to create the Crab Nebula. And I thought you said that happened in 1040.
1064.
Or that seems amazingly specific. How do you, that might be hard to answer, in a quick way, but how do you know that so specifically?
Because there were Chinese astronomers that they noticed. So that is the supernova in our own galaxy. They get so luminous that you can see them very easily with naked eye during the night. And I think that it was luminous enough to see it during the day. So we do have extremely good historical notes about the Crab Nebula when it exploded. So that is known, the year, very well known, probably the month too.
Wow, that's amazing. There wasn't a question there with Connie, but some comments. Thank you, Connie. Any other questions that anybody else? And you, like I said, feel free to unmute yourself if you'd rather do that instead of typing. Everybody's shy.
Is it possible that that this supernova, this neutron star merger, will produce elements that haven't been found on Earth?
Well, so of the periodic table, the only ones that the only spots that are empty are the unstable elements. So I don't think so. But also I also want to say that some of these elements, so we actually do have evidence that some of these neutron star mergers have happened in our own galaxy. Because if you study the sediments, the chemical composition of the sediments of the oceans, they do have an imprint of the elements produced by a neutron star merger, which is to say that sometimes to learn about the universe, we need to look deep down in our oceans. So some of these elements produced by neutron star mergers are a way to say that some of these elements are on Earth, because they already happen in our galaxy, and the elements just cascaded through our atmosphere and they are on Earth, which is another way of answering to your question.
And there were a couple.
So what? Yeah. Mm-hmm.
So let's see. Paul asked, I imagine the X-rays from the 2017 event are gravitationally redshifted. Can you use that information to put a constraint on the radius for the remnant, e.g. to determine?
Yeah, these X-rays are not gravitationally redshifted, and the reason is that they are produced very far away from the merger site. So the X-rays are coming from these jets that travel at the speed of light. So basically, they're produced so far away that the gravitational redshift is not important. But what you're saying is very true, that if we have a surviving black hole and that thing might be accreting some mass, like from an accretion disk or something, that is true, that if I could detect some X-rays from that black hole, then I should be able to say something about the places, the regions that are affected by strong gravity of the black hole. But I'm not sure.
Let's see, what potential new physics are you most excited about, which might result from these new observational capabilities?
Yeah, so gravitational waves allow us to perceive a part of the universe that we can't see. Why? Because they just don't see matter. They go through it, which is good and bad, because it's also why they're so hard to detect. So they can carry information from places from which photons can't escape. An example is that we do expect when a star collapses, this is also a place where we do expect gravitational waves to be formed and produced a lot, and in a way that would depend on how that star is dying. It is a moment where photons can't get out. Matter is so dense that there is no chance the photons can get out, but the gravitational waves can. So if I could detect these gravitational waves, I could solve the problem of how does core collapse happens in stars, for example. So this is to say that gravitational waves, they're really providing a completely orthogonal view of the universe, and it's hard to quantify what we will find with gravitational waves. We have literally a new window of investigation in the universe that we didn't have until 2015.
Oh, that's amazing. Jeff asks, what drew you to this part of astrophysics and to Cal Berkeley?
Yeah, so why do astrophysics? That's a great question. Fundamentally, because I love math. I love math and physics, and I've always been fascinated that we can use the language that we created on Earth, math. So math for me is a language, is how I talk physics, and we can apply it to very distant places in the universe, and it works. And it works remarkably well. So I've always had that fascination. And for me, studying astrophysics is also a way to remain a kid forever, because it allows me to play with my equations, play with thinking about what questions I want to answer. It allows me to be creative in ways that I don't think any other job could. And that's the main answer. I just fascinated by the universe, and less so by planet Earth. And what drew me to Cal? So I strongly believe in public education, and I exist as a scientist because I was extremely lucky to be able to have access to public education of good level. And for me, Berkeley and Cal is an example of how public education can reach the highest possible levels. And the students here are just wonderful and amazing, and they are just a joy to work with. And that's why I'm here. I want to do science at the maximum level, and I want to do it in a way that is accessible to everybody.
Awesome. Wonderful. Well, I don't see any more questions. Hopefully I got to everybody. And we're a little bit after 8. So unless anybody has another question they want to ask really quick, I think we're good. I want to thank you so much. Like I was telling you about Alex Filipenko, you made a very complex subject very obtainable and very easy, easier to understand. And yeah, it was wonderful. I really appreciate it. And I think everybody, I'm going to speak for everybody here. I'm sure everybody feels
Thank you so much. Yeah.
Thank you so much. And I hope you all have a good rest of your evening, and hope to, Raffaella, if you'd ever like to come up to the observatory, of course.
I was thinking about it. Yes. Yeah, I might come up. Yes. Thank you very much for having me. I love talking about my job. I love my job. So it was a great pleasure. Thank you so much.
Thank you. Thank you, everybody. Hope to see you soon. Bye-bye.